Hi everyone, this is the second video in the series of video lectures on application of machine learning to algorithmic trading. In this lecture, I will demonstrate how machine learning can be used, at least in theory, to predict price movements. In other words, I will show how the challenge of forecasting the prices of financial instruments can be framed as a machine learning task using tabular data. More specifically, the structure of this lecture will be as follows. First, I will demonstrate what classical or vanilla machine learning is. You will learn how to build a machine learning model with just a few lines of simple, easy to understand Python code using scikit-learn, the standard Python library for machine learning. Second, you will learn how to easily download stock price data with a single line of Python code using the Yahoo Finance library, no registration required. Third, you will learn how to create professional-looking visualizations of financial data using another Python library. Fourth, I will explain what technical indicators are and introduce a powerful Python library capable of calculating hundreds of standard financial indicators used in technical analysis. We will need them as features to be used as inputs for machine learning modeling. So let's start by building our first machine learning model using Python. Before we proceed, I would like to mention that all the code presented here is freely available on GitHub. The link is provided in the video description. As you can see on the screen, we start with importing all the libraries or specific objects from them that we plan to use later. While it is possible to import the libraries later as needed, it is considered good practice to import all of them at the beginning so it is clear to everyone which one are required. Note that you might first need to install some of these libraries, but that's very simple. You just need to run a single pip install command in your terminal. If you are unsure how to do this, there's plenty of information available online and it's easy to figure out. So let us look at what we import. The first four imports are from different modules of scikit-learn library. From the dataset module, we import fetch California housing. We will use this object to get prices of California houses used in our example to build a machine learning model capable of predicting prices of houses. Then we import train test split. We use this function to split our dataset into two parts, one for training of the model and another one for testing it. The next two lines are used to import different ML models, machine learning models, linear regression and decision trees in our case. Note that there are dozens of others, much more powerful models available in scikit-learn, like neural networks, random forest, XGBoost, and many others. After that, we import pandas library. This is a library for working with tables. We use it here only to display our data as a human-readable table. Finally, we import matplotlib library for making plots. We will use it to show how predictions, that is, predicted prices, relate to real prices. Once all the imports are done, we can proceed to loading the data. We load the entire California housing dataset with a single command using the fetch California housing function without any arguments. The returned object, which we name housing, contains a wealth of information. First, we extract the features table, which we call X, and the target column, which we call Y. Now let us examine the structure or shapes of our data objects. As we can see, X has over 2000 rows, with each row representing a specific house. It also has 8 columns corresponding to 8 different parameters or features of the houses. The target column contains over 2000 house prices. Each value in the target column corresponds to a row in the features table. To make this less abstract, we can look at the first 5 rows of the features table, focusing on just the first 4 columns. We avoid printing more rows or columns to keep the output clean and manageable. We also display the first 5 prices corresponding to the 5 printed rows of the features table. So let us now build our first machine learning model using the scikit-learn library. First, note that scikit-learn doesn't require the pandas table that we created earlier for visualization purposes. Instead, it works directly with the X and Y objects. To recap, X is a two-dimensional array or table containing the features, and Y is a one-dimensional array or column containing the targets or house prices in our case. We start by splitting the data objects X and Y into two parts. Some rows from the features table, along with their corresponding targets, will go into one dataset, which we will use to train the model. The remaining rows, along with their targets, will form another dataset, which we will use to test the trained model. Now we have everything we need to start training. First, we need to choose which model to use. Scikit-learn offers a wide range of advanced and powerful models. Just to name a few: neural networks, random forests, XGBoost, and many more. For our example, we will use a linear model and a decision tree. You can create a model object with just a single comment, as shown in cell 13. Once a model is created, we can start training it, which is also known as fitting. You can train a model with just a single line of code, as shown in cells 14 and 15. To train the model, we provide examples of features, X-train in our case, along with the corresponding examples of targets, Y-train in our case. Training the model is the core part of the machine learning section of this lecture, so let's take a moment to understand exactly what is happening here. Let us use the linear model as an example. In this model, predictions of the targets are calculated by a linear function, which means that we multiply the value of each feature by a feature-specific coefficient. After that, we sum up these products, or in other words, we sum up the scaled features. Finally, we shift this sum up or down by a specific fixed amount. The challenge is that at the beginning we don't know the values of the model parameters, the feature-specific coefficients, and the final shift in our case. So we use the data, that is features and their corresponding targets, to determine which values of the model parameters work best. In other words, during training we search for optimal values of model parameters that allow the model to reproduce the target values as accurately as possible. To summarize, we need training or fitting to find the optimal values of model parameters, or in our case, to find the best linear function. Now that the model is trained, it can be used to generate predictions. As shown in cell 16, we use both models to predict target values for feature table that were not seen during training. In our case, this means predicting prices for houses for which the actual price are unknown. Of course, these predictions won't exactly match the real prices for several reasons. First, prices are stochastic, meaning that even with identical values of the features, the actual price can vary. Second, the model is only an approximation of reality, and it can capture it only to a certain extent. The goal of a machine learning specialist is to find a model that captures reality as accurately as possible. Let us use the pandas library again to create a human-readable table that includes not only the features and targets as before, but also the two sets of predictions generated by our models. We start by using the 2D array of features to create the initial version of the table. To do this, we need to specify the column names, that is, the names of the features. Next, we add 3 additional columns, one for the target values and 2 for the predictions. Keep in mind that the models attempted to guess the target values without having access to them, using only the features values. To get an idea of how the predictions relate to the actual prices, let's plot them. We will use the matplotlib library, which is the standard Python library for creating plots. The x-axis represents the real values and the y-axis shows our model's predictions. Predictions from different models are displayed in different colors. As we can see in the figure, the models tend to predict higher values when the actual prices are higher. For now, we won't focus on the details of this relationship or on measuring accuracy, since our main goal is to present the core ideas. Now that we have learned the basics of machine learning, let's make our first attempt to apply this knowledge to the problem of trading. First and foremost, if we want to use machine learning, we need data. To obtain our initial dataset, we will use the Yahoo Finance library. Remember that, as with the libraries used earlier, you need to install it first using the pip install command. That's it, it is for free and you don't need to register. So we first import the library as shown in cell 31. In the next cell, we use the download method from the library to load Google stock prices. To load the data, you need to specify a ticker, which acts as the company's ID, along with the start and end dates. The data will be returned as a pandas table, also known as a data frame. Let's take a look at the datasets to see what it contains. To do that, we print the first 5 rows of the table. As we can see, the table contains 6 columns. The first column is the date. Open is the stock price at the moment the exchange opened on that date. Close is the price at the moment the exchange closed. Low and high represent the minimum and maximum prices respectively. Volume is the amount of stock traded at that date. Another very useful way to explore data is through visualization. I encourage you to always visualize the data rather than relying solely on raw numbers, as visuals often reveal patterns that might otherwise go unnoticed. There are well-established, time-tested ways to visualize financial data. To access this, we can use a specialized library. Yes, it seems like Python really does have a library for everything. First, we import the library, then we cut or reduce our dataset to include only data after June 1st, 2025. We do this to avoid overloading the image and to make it easier to see details such as prices on a specific date. We can control the content and style of the plot using various parameters as shown in cell 47. On the figure you see what are called candles. Each candle represents the 4 key prices, open, high, low and close, for a specific date. The color of the candle, white or black, indicates whether the close price was higher or lower than the open price. Now we have a dataset presented as a table, and we understand its structure, but where are the features and the target? At this point we don't have either. We need to create them. Let's start with the features. A feature is a number that in some sense compresses the history of prices. In other words, it is a value that can be calculated based on past price data. To make this concept clear, let's look at 3 examples of very simple features. First, we calculate a feature called range. To do this, we find the maximum and minimum closing price over the last 5 days, which defines an interval. Then we determine where the most recent closing price falls within that interval. This feature takes values between 0 and 1. A value of 0 means the most recent closing price is equal to the 5-day minimum. A value of 1 means that it matches the 5-day maximum. A value of 0.5 indicates the price is exactly in the middle of the 5-day interval. We call the second feature that we calculate close ratio. We define this feature as the close price averaged over the last 5 days divided by the close price averaged over the last 3 days. Finally, we calculate a feature that we call Sharp. To calculate this feature, we divide the close price average over the last 6 days by standard deviation of the close price calculated over the same period. We add the 3 features as new columns in our data table. As you can see, the first few values in these columns are none, which stands for not a number. This occurs because each feature is based on a window of previous prices, and for the earliest dates in the table, there isn't enough historical data available to compute them. Note that in our examples, we always used a window of past values and applied some sort of aggregation or compression, minimum, maximum, average, standard deviation. While this is a common approach, it's not the only way to define features. You will see other methods a bit later. Also keep in mind that the features we have introduced are for illustration purpose only. We don't claim that they are particularly strong or useful. You have just seen how to define your own features. With some creativity, you can come up with many very sophisticated and potentially very useful features. However, you might also want to explore features developed by the trading community over decades and proven through practical use. These features are known as technical indicators, and there are hundreds of them. Fortunately, there are several Python libraries that can calculate these indicators for you. Let's take a look at how that works. First, we import the library and then we add to the table new technical indicators one by one. In our example, we have added relative strength index, average true range, on-balance volume, commodity channel index, and volume-weighted average price. Note that some of the indicators use also volumes in addition to prices. Let us look at the last 7 rows of our dataset. On the right you see 5 new columns containing the added technical indicators. In machine learning terms, these indicators are our features. So now that we have our features, how do we get the targets? Intuitively, a target is something that we want the model to be able to predict. And what do we want to predict? Probably future price movements. For example, if we know that the price will go up tomorrow during the trading day, we would buy stocks at the beginning of the day with the intention of selling them at the end. Likewise, if we expect the price to go down, we would sell at the beginning of the day and buy back later when the price is lower. In that scenario, we calculate the relative price change as the difference between the close and open prices, divided by the open price. This value is typically multiplied by 100 to express the price change as a percentage. After calculating the relative price change, we need to shift them so that the target for today is the price change for tomorrow. In other words, we want to use today's features to predict tomorrow's price movement, so they have to be in the same row. Please note that we can also consider other scenarios. For example, we might try to profit from overnight price movements. In that case, the target, that is the price change, should be calculated differently, as the difference between tomorrow's open price and today's close price divided by today's close price. Now we have everything we need, features and target, to build a predictive model using machine learning. First, in cell 137, we remove unnecessary columns from the table, keeping only the features and their target. Next, we eliminate rows containing missing values. Then, in cell 138, we extract NumPy array or tensor from the pandas data frame, since that's the format expected by the scikit-learn library, as we have seen earlier. In cell 139, we split the dataset into two parts, one for training and one for testing. Unlike the housing price example, we do not split the data randomly, we split it chronologically. This is crucial in finance because neighboring rows represent consecutive trading days and are therefore not independent. They may contain similar patterns or behaviors and should remain in the same dataset to avoid data leakage. We will discuss this requirement in more detail later. Finally, in cell 140, we train or fit the model using the training dataset. Then, in cell 141, we use the trained model to make predictions on the test dataset. Let us examine our predictions. First, as before, we can plot the predicted values against the actual values. Unlike the housing price example, we don't see any clear relationship between the predictions and the real values. This is a common situation in price prediction for financial instruments. What we need to do now is to check if there is a dependency which is not obvious or not detectable with the naked eye. For that, we use statistical tests. The concept of a statistical test is extremely important in the context of algorithmic trading. A statistical test determines if we have enough evidence to believe that observed effect is real and not just a coincidence. For example, we might see in the data that, let's say, some means are slightly different, or a mean is slightly positive, or there is a small correlation between some features. In that case, we should make an assumption called null hypothesis that in reality those things do not exist or equal to zero. Then we ask ourselves how probable is it under the given assumption to observe what we have observed just by chance or by coincidence. This probability is called p-value. If this value is very small, we can reject the null hypothesis. In other words, we can say that our observation and our hypothesis contradict each other. In our case, we can start from a simple Pearson correlation, which comes with calculation of statistical significance or p-value. The observed correlation between real values and prediction is positive 0.06, but is it statistically significant? The p-value is about 10%, which means the result is not statistically significant. This is not surprising given that we used randomly chosen features, a small dataset, and a linear model which may not be well suited for our case. In this video, we took our first step towards bridging the gap between machine learning and algorithmic trading. The initial model we built didn't perform well. However, that doesn't mean our approach was incorrect. It was simply insufficient. We have moved in the right direction, but there is more work to be done and further steps to take. In the upcoming videos, you will learn how to properly measure the quality of your predictions, what exactly you should aim to predict, and how to use those predictions, specifically how much to buy or sell based on them, depending on what you are trying to optimize. If you learned something, please hit the like button. If you have any questions, suggestions or requests, feel free to leave them in the comments. I will do my best to read and respond to each one. And don't forget to subscribe so you don't miss any new videos. Thank you.